All right, continuing example 11.6, we were calculating the F2, this second force, okay? And we needed to plug in our numbers. So we have our F1, 500 newtons, divided by our area, which is going to be pi r squared, okay? And our radius, well, actually that should be divided by 2. This is our diameter is 0.5 centimeters, so we're going to divide that by 2 as well. Okay, and since it's in centimeters, actually we won't need to do that. So let me go ahead and erase that part. Oh, it won't let me erase. Okay. Get my pen, and I'll go ahead and just cross this out. Sorry about that confusion. The reason we don't need to convert it to meters is because we will have our area on top, and that'll cancel out our centimeters anyway. Okay, so we have 500 newtons divided by pi times our radius squared, which is 0.5 centimeters divided by 2. And so we'll have the same thing up here. Our area is going to be pi times r squared. Our radius is our diameter is 2.5 centimeters. And so we'll need to divide that by 2 as well. Okay? So, as you can see, our pi will cancel here and here. Okay? And then we can go ahead and plug this into our calculator. So we have 500 times 2.5 over 2, and that should be squared. And then we'll divide that by 0.5 over 2, and that should be squared as well. So our force here that we are left with is going to be 1.25 times 10 to the 4th, and this is in newtons. So this is our F2. Okay, I can't write it down there for some reason. F2. There we go. Okay. Alright, so this is the force that's created by, or at each of the wheel cylinders by that initial force. Okay? Alright. Now we want to look at different kinds of pressures. So there's one we call gauge pressure, and that's the pressure that's relative to atmospheric pressure. Okay? And this will be positive for pressures above atmospheric pressure and negative for pressures below it. Okay, so gauge pressure. Then we have absolute pressure, which is also called total pressure. Okay, it's going to be the sum of gauge pressure and atmospheric pressure. Okay, and since we are adding these two pressures, it will not be negative. Okay, it can't be negative, so always positive. Okay, then we have mechanical pressure gauges, and these are the pressures that result in a force that's converted into a readout. Okay, so we have a couple of examples down here. This is a mechanical pressure gauge in which a spring and a pivot, okay, are then converted from whatever the pressure is that's being measured into some kind of readout. Okay, there's also a mercury barometer, same kind of deal. We have some kind of pressure that gets measured through the barometer. Okay. All right, so let's go on with another example. Example 11.7. Intravenous infusions are usually made with the help of gravitational force, assuming that the density of the fluid being administered is 1 gram per milliliter. At what height should the IV bag be placed above the entry point so that the fluid just enters the vein if the blood pressure in the vein is 18 millimeters mercury above atmospheric pressure. Okay, and we're assuming that the IV bag is collapsible. Okay, so again, we are wanting to know what height should this bag be placed. Okay, so remember that pressure is equal to our height times our density times our acceleration due to gravity. Okay, and we want to know height. We know the density of the fluid. Okay, and we know the pressure, the blood pressure. Okay, so we want to know the height. That's going to be P over rho times G. We're going to need to probably go to our textbook. Let's go ahead and do that and figure out maybe some conversions if possible. So let's see. Okay. So we have some conversions here, and we have grams per milliliter squared, and we also have our pressure here is 18 millimeters. So we want to convert that pressure. Okay. So you see 1 atmosphere here. Conversion to pascals. Yeah, let's use that. Okay, so 1 millimeter is equal to 133 Newton per meter squared. So 133. Let me write that down real quick. So 1 mmHg is 133 pascals. Okay. And this is going to require a little bit of prior knowledge. So let me go ahead and get that together. Alright, so this density of fluid is just going to be 1 times 10 to the third kilogram per meters cubed. Okay, so our height is going to be equal to our blood pressure, which is 18 millimeter Hg, and we need to convert that. So that's going to be 133 pascals over 1 millimeter Hg. Okay, so that's going to be our pressure. We're going to divide that by our density. 1 times 10 to the third kilogram per meters cubed. And times our acceleration due to gravity, 9.8 meters per second squared. Okay. So let's go ahead and put that into our calculator. And we'll get a height of 0.244 meters. Okay. Or what would that be? About 24.4 centimeters. I don't know why I put about. It's the same thing. Okay. Alright, so that is example 11.7. Now let's move on to another principle, and that's called Archimedes Principle. And this is going to have to do with the idea of buoyancy. Okay, a buoyant force is going to be the net upward force on any object or fluid. Okay, and Archimedes' principle states that the buoyant force on an object equals the weight of the fluid it displaces. So here in this diagram we see that in picture form. Okay, so this is the free body diagram of this case. We have the object, okay, and the weight of that object in the fluid is going to be equal to that buoyant force. Okay, or I'm sorry, not the weight of the object, but you can see here this amount of fluid, okay, creates some kind of buoyant, or there's some kind of buoyant force acting on this object, okay, and then without that object, but this same area, the same volume here, okay, will have some weight of the fluid, okay, it has some weight, and that's going to be the same as the buoyant force on that volume. Okay, so compare these two, maybe pause the video, kind of look at them, make sure you understand it a little better. Okay, looking at this diagram, it may be a little bit confusing, but it might be helpful. Okay. Okay, so I'm going to go ahead and move on with our example here. Okay, so this is example 11.8. The first question, or the first part of this question, is to calculate the buoyant force on 10,000 metric tons, or 1 times 10 to the 7th kilograms of solid steel, which is completely submerged in water, and compare it with the steel's weight. Okay, so we are going to need to calculate the buoyant force, which is going to be FB, which is also going to be the weight of the fluid it displaces. Okay, so since we want to know the weight of the fluid, or the weight of the water, we're going to need to know the mass of the water. Okay, so what mass we need, or what mass of that water is, and then we will multiply it by gravity. Okay, so this is going to be a few different steps. So we need to find this mass of the water. Okay, our mass of water can be calculated through the knowledge that density is mass over volume. So we can say mass equals density times volume. Okay, but again, we don't know the volume of the water, but we're saying that we dropped this solid steel into the water. Okay, so we can find that volume. Okay, so what we need to do is find the volume of the steel. Okay. Okay, so we have the mass of the steel. Okay, and let's see, we can find the density of the steel. Okay, so we can say, let me see, volume. The volume of the steel will be the mass of the steel divided by the density of the steel. Okay, remember, density is mass over volume. Okay, so this is the equation that I just keep working with, and I keep manipulating. Okay, so the volume that is displaced by the steel will be the volume of the water that gets displaced. Okay, so that's the idea that I'm looking for. This should also equal the volume of the water. We'll see you in the next video.